Today we'll be showing you how to communicate to devices on DNP3 over Ethernet in a ControlLogix system using our MVI56E DNP net. The module can communicate simultaneously with DNP3 Ethernet clients or masters and up to 40 DNP3 Ethernet server devices such as RTUs, IEDs, and various protection relays. The MVI56E DNP net supports 300 user-definable commands and over 100,000 words or points of data. In this video, we're going to create a project in RSLogix 5000 or Studio 5000, depending on your version. The steps are the same. We'll import the supplied AOI. We'll then walk through the options to set up the module as a server or slave, communicating with a DNP client, typically a SCADA host. We'll wrap up by going over how to access the module's diagnostics using ProSoft Configuration Builder. If you wanted to see how to configure the DNP net to operate as a master, you should watch the DNP net client configuration video. To begin, we'll open up RSLogix 5000 and I'll create a new project. I'll define the processor, which in my case is an Allen Bradley 1756 L63 ControlLogix controller. I'll select the latest revision. I'll give it a name, identify the chassis type, and select the slot number that the ControlLogix processor occupies in the rack. I have a project folder already set up where I'm going to save the project files, but the default location's fine. So once the project's created, I'll expand the I/O configuration in the controller organizer. Right-click on the 1756 backplane and select New Module. I'll filter by Other and choose a generic 1756 module and click Create. In the New Module window, I'll give it a name. I'll call it My DNP Net just to make it distinctive. It's important at this point to set the COM format to data int so that the module can communicate over the backplane. The slot number should be the slot the DNP net occupies in the rack, and connection parameters should be set as seen here. This is pretty standard for the ControlLogix platform. When you're done, you can click OK, and if you do look under module properties, you can adjust the RPI. I'm just going to leave it at 5 milliseconds, and I can now see the module in the controller organizer window. Now we'll bring in the add-on instruction file and load it into the ladder. This aids in the configuration and setup of the module and also allows for the configuration data to be stored in the PAC ladder code. You can get the add-on instruction, which is an L5X file, off of the product disk, or you can download a copy by going to our website at www.prosoft-technology.com, locating the product page for the MVI56E DNP net, and looking under the Downloads tab. Once you have the AOI file, you go under Tasks, open Main Task, Main Program, and double-click on Main Routine. Right-click on Rung 0 and select Import Rung. Then browse for and select the .L5X add-on instruction file and click Import. When the Import configuration window opens, select Controller Tags and change the slot number by modifying the local slot number field to match the number of the slot where the MVI56E DNP net is residing in your rack. In this case, I have the module in slot 2, so I'll change each field to slot 2. Before we move on, we'll click the configuration dialog box next to both read Ethernet message and write Ethernet message to confirm that our communication path is valid. Select the Communication tab and confirm that your DNP net is named in the path field. If not, browse for and select your DNP net, click OK, and OK again. Once this is done, click OK, return to main routine and delete rung 0. The user-defined data types imported with the add-on instruction are now listed in the data type section of the controller organizer tree. User-defined data types, or UDTs, are used to organize the various types of data and control features that the module offers. We'll be taking a closer look at UDTs in a few minutes. For now, we can download the program to the processor. I'll go up to Communication and select Who Active. Locate the Ethernet module in the ControlLogix rack. Open up the backplane and select the processor and click Download. I'll click Download again on the download screen. The CPU will receive the configuration, and once the download's complete, we're given the option to place the controller in remote run mode. If the option doesn't come up automatically, you can go over to the controller status bar, be sure that you're online, and select Run Mode. We can now edit the configuration for the DNP3 Ethernet settings. To do this, we'll make some changes to the controller tags to assign a permanent IP address. Open up dnpnet.config.ip settings in the controller tags. You can read the current IP settings from the module by triggering the dnpnet.config.ip settings read tag. And if we do that, we'll see the tags for the IP, the net mask, and the gateway will all populate with the current IP settings. I can enter the IP address here that I want the module to use, as well as subnet mask and gateway parameters. And once I'm done making all the changes I need, I'll trigger the dnpnet.config IP settings.write tag by typing a 1, hitting enter, and this will send the parameters to the module. And you should see the new IP address appear on the module's LED scroll. Note that you may need to warm boot the module for the IP setting to be reflected on the network. To configure some aspects of the module, you edit the user-defined data types. As I mentioned earlier, the UDTs help to group and structure the variety and volume of data and features that the module offers. All data and control parameters related to the NVI56E DNPnet are contained in the UDTs. The DNPnet module def data type is the primary top-level data structure in which all other lower-order data types are grouped and organized. So essentially, all groups branch down from this UDT. And at this point, we need to determine if we're going to configure the NVI56E DNPnet module as a server or a client. For this video, we're going to configure the module as a server or slave on the DNP 3.0 network. I'll edit the DNP input and output database, and if I expand these, I can see the different data types that are available. Server mode is used when the module will serve data to a SCADA host or other master device. To configure the module as a client, you would edit the IED input and output data type, but we don't need to worry about that. For this video, we will only concern ourselves with the DNP input and output databases. Before getting started, I'll just go ahead and save my project. So now we'll take a look at how to configure the NVI56E DNPnet module as a server. To do this, we'll go down to the server tag, and this is where you'll find all the configuration options to configure the module to act as a server. So to begin with, we'll edit the user-defined data types for the DNP. There's an entry for input database at DNPnet, DNP input database, and you can see there's one for the DNP output data as well. So we'll need to take the processor offline to edit these. Double click on this, and here you can make edits to the database size for each data type. For this example, I'll lower my binary and analog arrays to 10. This is a word count, so for binary, this would mean 160 points of data. Typically, you'd want to keep the array size as low as is reasonable, considering your needs. The module can only pass 250 words of data across the backplane to the controller at a time, so if you can accommodate your data in one or two 250 word chunks, your data transfer will be significantly faster than if you need to transfer 10 or 12 chunks of 250 words. Now keep in mind that you're going to need to download the changed configuration before you can go back to run mode. It's important to have database sizing all squared away right from the beginning so that you don't have to interrupt your application once it's running. Now we'll take a quick look at the DNP server settings. For this, we'll go back to the controller tags. The internal server ID is the DNP address for the module. Messages from clients must point to this address in order for them to be processed by the module. The whitelist tag is used if you want to specify which IP address can access the module. If this is set to 0, then any device on the network can access the module. Setting it to 1 means that only messages from devices using IPs that are specified down here will be accepted by the module. The next several tags are where you configure how the module generates DNP3 events by setting the event class and the default deadband parameters for the module. Event messages are how the server reports a change event to a client device. This can include a timestamp of when the change occurred and can be either pulled by the client or reported unsolicited by the server. When the client polls the server for event data, it can do so by requesting data for individual classes or multiple classes. By default, binary inputs are class 1, analog 16 and 32-bit inputs are class 2, floats and double inputs are class 3. You can reassign the classes for each data type if you want, but the default setup is fine for most cases. I'm not going to change it. Next up are the tags, where you can define the default deadband for each of the data types. The deadband is a definable value used for the module to generate DNP3 events. Deadband refers to the margin of change in a value of a data point on a server device before an event is generated and stored in the event queue of the module. The event can then be pulled by a client by asking for class 1, 2, or 3 data. Or it can be sent to the client without the client having to pull for that event data as an unsolicited message. We'll return here later and I'll give a demonstration of how this works. While these parameters that we've just mentioned set event generation for all points in the module, it's also possible to specify a deadband value and a class for individual data points using the override feature shown here. For instance, if you had a point that you know will routinely vary by more than the value of the default deadband, and you don't want it to be generating events all the time, you could either change the default value to a larger number, or you could set an override for that point to something more appropriate. This allows you the flexibility to customize how frequently the DNPNet module will generate event data. The module can generate an event for any binary input which changes state, or any analog point which changes beyond the deadband setting for the point. If we expand the dnpnet.config.dnp server override tag, we can see there are tags for each of the data types. Under binary inputs, there are fields for point number, which is the point number index to be overwritten, and class, which is simply the class of the point number we specified up above. A value of 0 for the class will suppress event generation for that point, so keep that in mind. If we take a look at analog inputs, we'll again see point number and class, but we can also assign an actual deadband range for the point numbers we're overriding. These same fields are available in floats and double inputs as well. So we'll go on down to time sync tags. First up is analog input events with time. This is where you control whether or not analog input events generated by the module will include the time and date of the event. Setting this to 0 means that no time data will be included in the default object. A 1 means that the time of the event will be included in the default object. So a 1 is on, 0 is off. Next, we have events require time sync. This specifies whether or not the server will generate events when its time is not synchronized from a client. Setting this to 1 means the server will not generate an event until its time has been synchronized. Setting it to 0 means it will generate events without synchronization. So again, 1 is on, 0 is off. So that pretty much covers the bare essentials of a server configuration. Once the configuration is ready, we'll need to warm boot the module in order for the configuration to take effect. Just expand dnpnet.control.warmboot and enter a 1. This will warm boot the module, it will receive the new configuration and reboot. Let's take a look at the input data sent from the module to the SCADA system. Expand dnpnet.data.dmpin, and here you can see an array of all the different data types available under the server input UDT. The array sizes in the sample ladder should be sized according to the needs of your application. You'll remember that I resized them all to 10 in the UDTs earlier. The fewer the words of data to transfer between the ControlLogix processor and the module, the better the data update rate you'll see from the card. We'll simulate a DNP master using ASE 2000. At this point, the DNPnet module needs to be plugged into the network, and all polls will be addressed to the DNPnet's IP address. And we'll start by taking a look at how the 16-bit analog input data works. I've entered some values under dnpnet.data.dmpin analog 16. I'll switch over to ASE 2000 where I have a poll for analog data ready to go. And there are the data points from our DNPnet slave. So the input data is working properly. So now would probably be a good time to note the structure of the Object30 database in the DNPnet module. It's important to note that all the analog input data, including floats, are stored together with the starting address for one type beginning where another type ends. So if your database for 16-bit analog input data is 100, it would run from 0 to 99 in the module database. Then the database for the 32-bit analog data would begin at 100. If that is sized to 100, it would run from 100 to 199, and your float data would begin at 200. If you have 50 short floats, then your long float data would begin at 250, and so on. This order applies however the databases for each data type are sized. If, for example, I resized my 16-bit analog input data to 10, then it would go from 0 to 9, and the 32-bit data would begin at 10. Binary and counter data types each have their own databases, so this only applies to analog data. Now, I'll enter a value in ASE 2000 to illustrate where output data appears. So the value will be written to the third word in the analog output array. The value will be 871. Now we'll jump back to RSLogix to see the output data coming from the master to our DNPnet. Expand dnpnet.data.dnpout. We'll open up analog 16-bit data, and there's the value. So next we'll take a quick look at how binary data looks in the tags. I'll drill down to dmpnet.data, dmp in binary, open up tag 0 and change some bits. Now you can see that I have 1 entered on the first 3 bits and on the last bit in the word. Now I'll go back over to ASE 2000 and I'll pull for binary data. You can see that the first 3 bits are right there and the 16th bit right there. Pretty straightforward. Now we'll run through an example of event data. For this one, we're going to return to the dmpnet.config.dnp3 server tags. Open this up, go down, and I'm going to set the deadband value for analog 16-bit inputs to 100. If an analog input value changes by a value of 100 or more, it will trigger an event message for that point. So let's try it out. I'll go back to DNP in tags and open up the analog 16 tags. I'll go down a little ways and enter a value of 99 into the 8th point. And looking at my master simulator in ASE 2000, no events have been generated. If I go back and change that point to 100 and break the deadband, now an event has been generated, and I can see the point number and the value as well. There's also a timestamp for the event. Now once a point breaks deadband, generating an event, it then resets the deadband at that value. So this point would have to go back down to 0 or up to 200 in order for it to generate another event. Finally, we'll take a look at the status tags. This status data is returned on each read block and can be used to detect proper module operation. For this example, I'll just focus on the general stat tag, where you'll find a wide range of general status information, including error counts and block errors. For more diagnostic information, we can take a look at the DNPnet module in ProSoft Configuration Builder. ProSoft Configuration Builder provides diagnostic information for debugging and troubleshooting. So I'll open up PCB and I'll select the default module in the tree view, right-click to open a shortcut menu, select Choose Module Type, which opens the Choose Module Type dialog box. Under Product Line Filter, select MVI56E, and in the Select Module Type drop-down list, I'll go down to the MVI56E DNPnet. Click OK to save your settings and return to the ProSoft Configuration Builder window. I'll right-click on the module again and choose Diagnostics. This will open the Diagnostics window. Click the Setup Connection button. In the connection setup window, with Ethernet set as the connection type, we'll enter the IP address that we assigned to the module. I'll hit Test Connection to verify that the module is accessible with the current settings, and if the test succeeds, I'll click Connect. On the diagnostic menu, the module information is arranged in a tree structure here over on the left. Expanding module. Under Info, you can see the module information. Under Block Status, you can see backplane information, including total blocks, total errors, as well as the number of read and write words. We can see the module database configuration by looking at the DNP points count and the IED points count. So if you want to double check your configuration, you can do so here. Moving down to DNP3 server, we can see the COM stats as well as socket status. And then under DNP3 client, we can see the COM status, server errors, and the client command list. Those are the basics of the MVI56E DNPNet module. There is a whole host of additional features and options that we didn't touch on here. If you'd like to know more about that, or if you have any questions about what you've seen here, don't hesitate to visit our website at www.prosoft-technology.com, or you can type in this address to go directly to the DNPNet product page. Until next time, happy training.